Hello everyone. This is a supplementary video for Project 2 for AA228, CS238, Decision Making Under Uncertainty, Fall 2018 with Michael Kuchenderfer. I'm Shushman, one of your TAs, and you've probably seen me if you've seen one of these videos before, you kind of know how this goes. This is fairly freestyle, and I haven't really rehearsed this, and I won't be doing much post-editing, so in advance, I apologize for any bloopers. My goal with this video, like with the previous one, if you watched it on the Bayesian structure learning project, is to give you an overview of some of the important and useful things to help you do project 2, and just to make that process a less painful one for you, hopefully. Before I get into it, I may not have made this very clear last time, but I want to make this crystal clear this time. Please start early. I cannot stress this enough. There are people who began 2 days before the deadline, and needless to say, they did not have a great experience. So, I've released this video about 10 days before, 9-10 days before the deadline. So that should hopefully give you some time, give you enough time to really get started and do a good job on this project, especially if you have trouble with project 1. So my goal with this video, so project 2, as you know, is on reinforcement learning specifically, and this will become relevant in a little bit. It's on batch reinforcement learning. The idea here is typically in a lot of papers that you will read on reinforcement learning, and I should state that a lot of this video is as much for your general edification as it is for hints on the homework. So please, watch it with an open mind. In a lot of settings, typically you have a simulator, either something from maybe OpenAI, which is actually one of the ones that we use for the data for Medium, is what we use for the data for Medium, or it could be in robotics. Often there's Mojoko is a simulator that's used, or just some self-made one that you've created. However, in this setting, or rather in this simulator, you can interact with it. So this is your algorithm. Your algorithm can take actions and get back reward and next state from some state, comma action, and get reward next state, and then you can run your RL algorithm here. However, in this homework, we don't have that setting. In this homework, what we have is we have a batch of data given to us already, batch of data that's given in the form S, A, R, S prime. And again, S, A, R, S prime. And if you've looked at the structure, you'll typically see that this S prime is just this S, but not necessarily, especially when episodes end. When episodes end, the next S might be a new one. So that's just something to keep in mind. So anyway, that's where this comes up. I will talk about in a little bit, but it's just something. It's a setting difference that you guys should keep in mind. So anyway, I will discuss briefly the 3 kinds of problem files that we have, and just like the homework itself, I'll talk about 3 aspects of them that sort of build up, and that are all useful for real-world reinforcement learning settings. So with small, the idea is just to discuss briefly how you do like a normal or a simple, basically model-based or model-free. I'll talk a little bit about both of them, but model-free RL with no there's no you don't have to do anything particularly special. You just have to implement what's in the book, just essentially line for line, and you should get a perfectly reasonable policy. So I'll use that small as like a baseline, but in many real world problems, you have larger state spaces. You don't necessarily see all the data, and so the medium and the large are kind of there to help you or force you to think about those settings. And I will, while discussing the medium and large problems, I will focus on certain things. which are generally useful for real-world large reinforcement learning problems. So in the medium, I'll talk a little bit about function approximation, which is generally useful. And with the large, I'll use the large to talk a little bit about exploiting structure. And actually, both medium and large will have a role, or rather exploiting structure will have a role for both medium and large. But I will, in particular, it's particularly true for the large problem, exploiting structure. And actually, and this will become more clear later on, you might not want to necessarily just do function approximation for the large one. And I'll talk a little bit about whether that seems reasonable to do or not. So again, I'll jump right in to talking about the small one. As I say in the description of the video, I'll assume that you are familiar with the project, that you've read the descriptions on the project website, and that you've had some time to go through at least the CSV files. So I do assume that you've done that, and so this is a supplementary video for that reason. It would also be nice if you refer along to chapter 5 of DMU. In particular, if you need to tag bookmarks, I'll be referring to algorithm 5.3 on page 123, and some text around it, so plus minus 3 pages. That's kind of the base point, and then yeah, so I think that plus minus 3 pages is pretty. Actually, my bad. Algorithm 5.3 and algorithm 5.2. Let's mention both of these, and both of these plus minus 3 pages. So I'll be discussing content that's around that area, so you might want to just follow along there. So jumping right into small, which has been provided essentially for you to just test out being able to implement a straightforward application of model-based or model-free RL and just see that it works reasonably, which it will. So what do we know about small CSV? We know that it's a grid world, and you should be somewhat familiar with grid world by now. But we haven't told you the parameters, so hidden parameters. We haven't necessarily told you those parameters. You'll have to estimate them, and that's the whole point of the RL. A reminder, and this is rather important. If you knew R and T and then did value iteration, that is not reinforcement learning. That is, oops, rainbow again. Get rid of that. That is planning, or with an MDP, or solving an MDP. I just want to make this clear from the outset, because a lot of even contemporary papers will often conflate these two terms, reinforcement learning and planning. But broadly, and Michael goes over a little about this in, I think, in chapter 1 or the preamble of DMU, where he talks about the difference between these things. So please be, and that's why RL is called model uncertainty, which is where you are not sure what R and what T are. You're not sure what they are. And so you can either assume a form for them, which is model based, or you can directly try to get a policy, which is the end goal of reinforcement learning, through a model free approach, just by looking at the data. But I just wanted to make this clear, because this, these terms can often be conflated, and I've come across this as well at, when I've been talking to other researchers. So I just want to, so there's one thing that you really should take away from like the preamble to all of this. It's understanding when to call it planning with an MDP or solving an MDP, and when we call it reinforcement learning. But anyway, so now jumping into small, you know that it's a, oops, let me bring that up again. You know that it's a grid world, but you don't know the parameters. You know that it's, well, you don't know the TNR unknown. You do know that it's a 10 cross 10 grid world, and because it's a grid world that there are 4 actions that are for up, down, left, right. Probably shouldn't have used lines here, but such is life. 4 actions for these settings. So you do know this, and you know that in the data, like this is represented by numbers 1 to 100, so there are 100 states, and then this is represented by numbers 1 to 4, so there are 4 actions. So you know that, and then the data of course reflects that. So I'll just quickly write out some data here so that we have something to work with. And this is actually data that's in the small.csv. I may have made some of this up, but anyway, let's see. Just going to write out just 5, like I did with the Bayesian count. I'm just going to talk a little bit about what you do with some of these records and then some of these data points, and then that should help you figure out what to do in general. All right. So this is some data where, as you know, this is S, this is A, this is R, and this is S prime. And the goal is to come up with the policy, and that does well. On this problem, note that we ask you to submit .policy files. I need to mention this because Gmail, oh well. Hopefully we can get that out of the way, but otherwise it's just a red herring. Oh, no, it's gone. So the policy file is not a special file. Someone had an issue with .gph, and they had an issue with .gph extensions, so it's not a special file, it's just a text file. So if this wasn't clear already, anyway, let me just get rid of that. It's a text file where, you know, if this is line 1, line 2, blah, 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 line 100, this is just the action that your policy should take. You know, action in state 1, action in state 2. And when we simulate this, we will generate a random start state, so S0 between 1 and 100. 1 and 100. Well, it's actually between 100, not either 1 and 100, but anyway, some abusive notation. We will then, for that S0, we will look up the corresponding line number S0. We'll see the action AS0. We'll take that action AS0. We'll run it through the grid world simulator. We'll get a new state S1. We'll then look up your action for S1, AS1, and then we'll run that again. And this is how we'll evaluate your policy for some number of rollouts, some number of Monte Carlo simulations. So your policy just has to give us that mapping from state to action. So the policy is a mapping from state to action. One thing to keep in mind is that this is we are asking you for a deterministic policy, where pi of s is some action. You could, you know, in some cases you might have a stochastic policy where pi of s is a some distribution over actions, but in this case we just want a deterministic policy. Just note down this data. I have it on a side note, so I'll be referring to it, but just note that down as we go further down the notebook. So yeah, so that's just a couple of things to mention there. Now, we have been given a lot of this data and we want to figure out a policy, right? First, let's try to do it the model-based RL. And for this, I want you to look along with section 5.2 of DMU. So the idea of model-based RL is to essentially estimate the transition functions and the reward functions. The reward function, rather. And here I'll talk about maximum likelihood estimation based RL, but you could in principle use something else. You could use some other parametric form for the you could have like where the transition is some parametric form, and some parametric form of SA of S prime, and R is some parametric form of SNA, but or something more general. Like you would do a bunch of things, but in this case we're just going to represent it using counts. And we can do that in this specific case. We can do that because the size of the state space for small is 100, the size of the action space is 4. So if you think about the transition matrix, it's 100 cross 4 cross 100, right? Because transition is it's S to A, S cross A cross S to something in 0, 1, which represents the probability of reaching state S prime if we're in state S and take action A, right? And so that's a 100 cross 4 cross 100 matrix, where if you talk about in coding terms, the Sth Ath S primeth entry of TS is just this value, right? And programmatically, we will obtain this value by counting from the data set D. This is the data set, by the way, that's been given to us. Similarly, the R matrix, which in the most general case, the R is actually a function of SA and S prime. So, to be most general, you might want to do it that way. But if you're using the book as stated, you don't have to worry about that. You can just compute the average. So I'll talk about that in a second. So R is a function from SA to real. So this RSA is is basically RSA. Okay, that was somewhat facetious, but and these two matrices in the model-based RL way of doing small are obtained by counting and averaging. And this is where, if you just walk through the data and implement equations 5.7 through 5.9 in DMU, you'll see how that works. And I'll just do that briefly here. So initialize T and R to be matrices, to be 0 matrices of 100 cross 4 cross 100 and 100 cross 4. You know that, so essentially, in this case, we tell you that you can obtain the index of a certain state by doing linear indices or int to xy, but you don't really need to know that, right? So for example, if we see the following transition, 33, 32, when you look at this, all you need to do is, based on equation 5.7 to 5.9, again, first you increment the count of n 33 1 plus plus, because that's just the count, right? You could have this in a separate array. You could do a running average. Because you also need to increment n 33 1 32 plus plus, right? So because you've seen 33 1 and you've seen 33 1 32, you increment those two counts, and then once you eventually once you've done this for all the data, you would get T33, let me do it matrix wise, 33 1 32, which is what you need, which is P of S prime equals 32 given S equals 33 32 A equals 1. You would just get this by literally dividing by doing that, right? And this just follows from the law of probability, right? Because just by the law of probability, this is the probability of seeing S prime equals 30. Oh, did I mess this up? I'm sorry. This will be 32 and this will be 33. Ah, there's another blooper right there. S prime equals 32 given S equals 33, A equals 1. Oh, actually, yeah. This is just by law of probability, right? Just by the basic definition, just by the conditional probability. And so these will obviously be just the counts. So n divided by the total count of the data set, and n of a smaller one divided by the total count of the data set. So that, and Okay, yeah, that's not helpful. And so there and then there. So, and this way you can get the average transition probability, and you know you see here why all the values along one hyperaxis will add up to 1, because we know that summation over all possible s primes n s a s prime is equal to n s a. This is just equation 5.7. So just based on that, we know that just by following those rules, this will be equal to 1, just by that relation. And if this is not clear, just go back and loop through and think about this again, and this will become clear to you. So this respects the transition matrix respects what we want from it. For the reward, it's a similar idea. Let's go back here. So 33.1, 0 was the reward. So we just did our, well, row, if you're following along from the book, 33, let me see if I can, yeah, 33.1 plus equals 0, right? And you've already incremented NSA here, so at the very end, after you do this through all the data, you would compute R33.1 equal to just the average of whatever you've seen all this while, right? And you have all of this information. This is just the average reward, which is what my maximum likelihood estimate tries to find. So yeah, so if you have these two matrices, you can just go through the data and you can just increment those things. The point to note here is you don't, I mean, you know there are 4 actions, right? So like 1, 2, 3, 4, and you know that they somehow correspond to up, down, left, right, but you don't need to know the correspondence. Don't need to know this. For small at least, because you can just count them up. You also don't actually, in principle, you don't need to know the relationship between from s to x comma y, like from 1 to 100, oops, to like 1 comma 1 to 10 comma 10. You don't actually need to know that, because you can just loop through the data, compute those TNR matrices, and then once you have the TNR matrices, once you have TNR, right, you can just use value iteration or policy iteration based on the algorithms in chapter 4. Whether you do it in matrix form, whether in iterative form, you can just do that, and you can get a policy that maps state 1 to 100 to the actions 1 to 4. You do this in the model-based setting, and you get something. So if you actually go ahead and implement this in this way, you create these matrices, count up these values, implement value iteration in matrix form or in iterative form, and you get the value and the corresponding policy, you'll be fine. You'll see yourself getting a reasonably good score. I'll make a quick comment on the model. So that was model based. I'll make a quick comment on the model free. Specifically, I'll talk about Q-learning, although you could use something else. So one thing to note here, and this is why I brought this up before, is if you look at algorithm 5.3, look at line 6. This is assuming you know what Q-learning is. I'm not going to be, you should know this for this video. I'm not saying that it's a bad thing if you don't know it for this video, but I'm not going to be explaining it in detail itself. But the point is, if you look at line 6, it says choose a T based on exploration strategy. And we talked about this, Michael talked about this in class. The whole point of reinforcement learning is, well, one point of reinforcement learning is to explore the different actions you could take to kind of figure out which are the good actions you should take. But this needs a simulator. And this brings us back to the point I was discussing earlier. Let's see if I can find this again. This idea of oops, oh, that's a while ago. Yeah, this idea of a simulator, right? So we don't have that. So you can't You've just given a batch of data and you have to figure out what you have to do. Let me zoom out there. We don't have that here. So in some sense, the action has been chosen for you by the data, right? Because we have S, A, R, S prime. You can't choose which A to take. It's been chosen for you. And that's where we talk about batch reinforcement learning. Because we've given you a batch of data. We haven't given you a simulator. Now, note that this isn't really a problem in model-based, because model-based is all about actually counting up occurrences, estimating an RNT, and then solving, validation, policy iteration with that to get a policy. But in Q-learning, in this case, actually, it makes your life easier in some way, because you don't need to implement, don't need to implement an exploration strategy. You just use exploration lines. So in algorithm 5.3, lines 6 and 7 are done for you. You already have an action and you have the next state. So you can just go to you can just jump to implementing line 8, which is the Q function update. And in terms of how you would actually implement this, so note that Q is a function of S and the state and the action, so it's the action value function to R. So you can have a Q matrix like this, 100 here and then 4 here. This is the actions, these are the states, and then you could literally just, that's you could initialize everything with 0, blah blah blah, and then for example, if you see the data point 33, 1, 0, 32. I realize I'm not really using the other examples, so maybe I could have just given you one. Psych. You could just do the update of line 8, the Q update. Upon observing this data, you would update Q matrix for 33, 1 according to the update. I'm not going to go through that because, well, actually, let me write that out. SA is updated by the previous value, which you'll look up from the matrix, plus some learning rate, plus the reward, in this case it's 0, plus the discount factor, max A prime, Q S prime, oh wait, this is infinite, yay, minus Q SA. So this is from the matrix you have already, you'll begin with some values, this is the same thing, this is a hyperparameter, that's 0, this is the discount, and then this just go back to the matrix. Yeah, back to the matrix, so that could be a movie title. And then you just, for a certain state S prime, you just look through the actions and choose the max one, right? And then you just keep doing that. And again, if you just implement this for the small, and you get the QSAs, and then remember the optimal policy for state S is just max, well, argmax, I should say. And this is the one you obtain on convergence. So you just pick up, the final matrix, another movie title, you just pick up the one that's maximum for each state, and then you get your action. So yeah, so that, if you just directly implement that and you just directly implement Q-learning for the small problem, you should be good. And just like if you directly implement model-based RL, maximum likelihood model-based RL, you should be good there as well. So yeah, that's all I have to say about the small problem. Like before, I've used up most of the time I wanted to take, so which you might say, oh hey, I was having trouble with the medium and large, but well, haha, that's the challenge. So I won't be as explicit or as detailed for the medium and large, but I will give you some hints. So you'll notice immediately with the medium problem, two things start coming up. You have a much larger state space. I think it's 50,000. And then you have a lot of unseen transitions. Like there are a lot of state actions, S prime things you just don't see in the data. And that's a problem, and that will be a problem in general for a lot of real world reinforcement learning settings. And then, there are a bunch of different ways to deal with that. I'll mostly talk about two. The first relies on the assumption, and they're somewhat related in some sense for this specific problem. As you know, this is a mountain car problem, so it's based on some physical, it has some physical significance. You know that the state is somehow a function of position and velocity, right? We haven't told you, I mean, we've given you some relationship between the state index and the position and velocity, uh, but we haven't exactly spelled it out for you. But the point is, you know that the state is some function of position and velocity, right? Um, so what that means is, since it's a physics-based problem, you can kind of, and also you know that the action is basically some acceleration in some sense. Um, you kind of know that S prime will be somewhat close to S, right? I mean, as long as these are physically reasonable things, S prime won't be that far away from S. So this whole mapping of S cross A to S prime, um, for a given SA, this will be pretty sparse, because for most states S prime, the probability of going to S prime for some particular S and A will be 0, because it's just too far away from what, however it's encoded. You don't necessarily know that, but you don't necessarily need to. However it's encoded will be pretty far away. So instead, I mean, you could still, depending on the size of the machine, although that's not what we're trying to optimize here, you could probably, in principle, uh, um, implement a 50,000 cross. How many actions are there? I think 9 actions. Oh, actually, oops, let me look that up. This is real-time error debugging. Yeah, so there are 7 actions, so 7 cross, you should just fast forward that out. I'm not going to edit it. You could try and define this matrix, but this would be very, very sparse, and you might not find it worth your while. So what you could instead do, and this is just a suggestion, not saying that you should do this, you could set it up so that S prime is some, nonlinear function of SA, and these can just use the indices. You don't even necessarily have to decode, just use the indices, like 1 to 50,000 and 1 to 7. These don't necessarily, you don't necessarily have to encode the underlying thing, because remember, if you, assuming we've done some reasonable indexing, right? Some scale, some affine transformation of the position and the velocity, and then they're multiplied. If you feed it a bunch of this data from the data set, and if this is some nonlinear regressor, which you can look up online how to do that, they should learn something pretty reasonable, right? It would probably learn like some, like some nonlinear sort of, it would be some like C1 times, or rather, maybe it'll be C1 times S square plus C2 times S plus C3 times A plus C4 times AS. Maybe it's something crazy like that, but you can just let some function optimizer, some function approximator figure that out and give you a good bunch of coefficients. And then what you can do is, essentially, you can just, once you have this some learned function approximator, you could just, given some SA, you could just make it so that transition of S prime AS is 1 if S prime equals F S comma A and 0 otherwise. Or, if you, which basically means this is the prediction of your thing, and it's predicting that's going to be the next state. You might need to round it off accordingly, but you could do that. If you're not comfortable with assigning it all the probability, what you could instead do is maybe give this like 0.9 and give everything else 1 by 0.1 by whatever, 49,999, or something like that, depending on how much you trust your regressor. But then this would be a valid, technically this would be a valid transition, and then you wouldn't need the explicit matrix. In this case, you would not do it in matrix form. You would just do it iteratively, and you would compute. So this is, in this case, I'm talking about value iteration and policy, or rather, I'm talking about model based, of course. You would just do it iteratively without explicitly representing the matrix. So that could be one thing to think about. For in model free, okay, before I get to model free, with reward, the only thing I'll say here is that you know that it has to reach the flag. So you know that there's only positive reward at certain states. Oh man, Gmail, you're really messing with me today. So that's all I'd say on this, but you should be able to actually exploit that structure. For model free, you don't really have the problem of a 50,000 cross 7 matrix. You just have a Q matrix of 50K cross 7. So you can probably think of still having a Q matrix. You will still have a lot of problem of unseen data, and so in that case you might want to think about approximating the Q matrix. And I won't go into this in detail, but you can look up stuff online for trying to approximate the Q function. You can also look at chapter 4, and Michael talks about approximate dynamic programming. Again, because this is a physical problem, physics-based problem, there's a reasonable amount of continuity or you can expect a reasonable amount of continuity in the Q function space. Basically, if two states are nearby, which they likely are if their indices are close to each other, and you take similar actions, they're probably not likely to have vastly different Q functions. There might be some finagling you need to do in regions close to the reward, but I'll let you think about that. So those are some of the hints I'll give for medium. And people have been having degrees of success with medium already, so I don't anticipate that being too much of a problem. Finally, the large. With the large, it's really all about structure. That's the key. And the point, the larger point, not intended, is the idea of using domain knowledge or intuition to decompose large problems. And this is an interesting and important aspect of real-world problem solving, MDP problem solving. And quick plug, I'll talk a little bit more about this on my lecture on hierarchical planning, which is on the 27th. So just a little plug for me. Oops, we're low on battery. All right. You should probably pause or fast forward this while I connect the charger, because I'm not going to restart this. Whew, crisis averted. All right, so oops, I do not need to be up to date with Windows. That will put us out of commission forever. So anyway, that's a quick plug for a lecture that I'll be doing. Let me snooze this here. On hierarchical planning, I talk about this a little bit more. But in this case, you don't have domain knowledge because we've been a little cruel and we haven't told you what the domain is. But you can figure out some useful stuff by looking at the data. I won't say too much more because it's a secret problem, and honestly, if you actually just directly applied Q-learning, you probably would get something reasonable anyway, I think. It would be suboptimal, it definitely wouldn't be close to optimal, but it would be good enough to get a positive score. So I won't say too much here, but I will say look at the data and don't just blindly approximate the value function. Oops. Blindly approximate. This approximation will not necessarily work well if the space is very discontinuous. So when you that might very well be the case here. And actually, if you look at the data, you'll see that there is some weird, at least in terms of the state indices, just just based on the closeness of the state indices, there isn't necessarily a continuity there. So you want to be careful. You want to be careful about how you approximate. So I'll say that. And the other thing that I'll say is, yeah. So if you look, let's just look at one transition here from the data set. Just look carefully. Actually, let me put one more. Yeah, I'm using more than one example. Just look at what's changing. It takes an action. There's just a change here. Now this in of itself might not mean anything necessarily, but if you squint hard enough at the data, you'll probably find some hidden structure that you might want to use. Again, since you don't know the domain, you have no idea what it's about, which typically won't be the case. In real problems, you'll at least have some idea. You'll at least know the system you're dealing with. You'll at least have some idea of the control space, of the state space, which again is what I'll talk more about in the lecture on hierarchical planning. But nevertheless, even for this problem, if you look at the transitions, you look at the ones that accrue high reward or the ones that accrue some positive reward, you should hopefully be able to figure out what in the state index relates to good rewards, what in the action index relates to good rewards. And if you even use that to some extent to inform, you could use that to as an initializer of your Q values, or an initializer of your V if you're doing value iteration. If you just use your in-domain knowledge from observing the data here, that actually might be enough to get you a reasonably good policy. But if you squint even more closely, you might actually be able to uncover the hidden structure and actually come up with a truly optimal policy that visits some very high reward states. I think you'll see some places have a reward like 200. And so you'll be able to figure out how to visit those. But anyway, that's not necessary to get full credit, and this should be enough. If you just look carefully at the states and figure out some patterns, that should actually be enough to get you on the path to getting full credit. So yeah, that's mostly what I had. I apologize for the little pause in between while I had to charge the Surface. So just to recap, I'm just going to go all the way to the top, although I know this is a video, so you can just go back and see it. Oops. Oh my goodness. Oh, and the zoom stopped working also. Just to recap, the idea with small was to think about just normal model-based RL versus model-free, and I talked a little bit about that. And then I gave some suggestions for function approximation and structure exploitation for the medium and large, and hopefully that should help you get across the finish line. So yeah, thanks for listening, and I hope this video is useful to some of you. All right, thanks guys.